Hi, so welcome back. In the first video here, we're going to be talking about how we're actually going to represent planning problems. So you, or at least someone, is asking of you to solve a real world problem, and we're going to try to translate into the language of planning. So there are many examples. I think one of the most basics, the fundamental ones that we'll talk about in this pathfinding domain, is something like you're dropped into a grid, into a maze, right? So within this maze, you're dropped in at some form of start location, and your goal here is, well, to go find an exit or to a goal location. Other really common examples of planning problems are things like, for example, solving Rubik's Cubes. The sliding tile puzzle is another one where you are trying to slide them around to get your numbers 1 to 9. Things like this. But otherwise, we're going to be, I think, using the maze problem to discuss how we're going to talk about this. Within the world of planning, we need to represent this using vocabulary and terms that make sense in the world of search, right? So we're going to be talking about states, actions, the goal test function, and then what constitutes an actual plan, as well as what your objectives are, because that changes how you're going to solve the problem. The first thing we need to know here is we need to come up with a way to describe our observations about the world, right? Where are we? What are the facts that are true about this current situation, about this current state, right? So the first thing we're talking about is states, and this is essentially a description of your position, okay? So like, I'm saying position in this sense more because I'm using the pathfinding example, but it's a description of the world. It's a set of facts that are true. And then we're going to be transitioning from some start location we begin inside the maze, and we're trying to go to a goal location, right? So there's an initial state and there's a goal state. Okay. So then we need to talk about what is a state? Sure, I call it a state, but we need a way to actually translate this into a description. So within a pathfinding example, the very common practice then is, let's talk about it in terms of an XY location, right? So otherwise, for S is then described as, if we give this a numbering system, 1, 2, 3, 4, the start location then is at A4, right? And then the goal is similarly at C1. Okay, so it's a pretty distinct way to represent a state, where we are in the world. Of course, you can incorporate as much information as you need depending on the real world problem. This is just a very simple example. And now we move on to the idea of solving the problem, right? So we're in some form of initial state. You know when you're dropped into a maze, you now have some decisions to make. Where are we going to go, right? So in the end, we're looking for some path that's going to connect them, right? But at the beginning, you drop into a maze and you have to see, what is available to me? You could move up. You could move from north, east. Sometimes, depending on the world state, right, you're going to have to define what actions are legal. Diagonals may be legal. In this simple example, I'm just going to keep it with just the cardinal directions, which we're going to call rectilinear. So you can only go north, east, south, or west, right? So your actions here from your start location is only going to be available as we're either moving north or east, right? So actions essentially describe what we can do, right? What can we do in the world? So you are essentially looking for transitions between states. Actions will transform you from one state to another, okay? And then we'll kind of skip slightly ahead here, and what we're trying to look for in the end is, of course, a full plan, a full path, right, from our start to the goal. Now, your plan is going to be composed then of a sequence of actions, right? Sequence of actions. This is essentially what actions and things can I do in my environment to take me from the start to the goal location. what I've skipped here is, of course, the goal test, right? So we know that in the interim, when you're taking actions, at some point we know that we need to stop. So even though you and I can go, hey, great, we're at the goal location, we need to inform our algorithms. They need to know and identify this as a special location, right? So this is essentially what the goal test function, which is an integral part of pathfinding algorithms and in heuristic search, like essentially, when are we done? Right, have we made it where we wanted to go? So our goal test often would be, maybe there's not always just one goal either, right? Maybe you're meant to be going to multiple parts of a maze. So the way this is translated is essentially that we can list a sequence of goals. So your goal test will just take your current coordinates, your current x, your current y, and check, hey, is this one of our terminal states? If so, we'll return true, and we know that we can finally stop. What we'll be returning is a plan, okay? So let's talk about it here. I think we'll kind of go back quickly, right? But the actions would be something like north, south, east, west. These are the things we can do in the world. But then we also have the idea that a plan now, a plan from, let's call it pi. A plan is going to be a sequence of actions that we can take, or alternatively, you can also write this just as the states themselves. So what I'm going to write here then is that we begin at some s, right, and then we're going to talk about the positions you move to. So it'll be some sequence of nodes, some sequence of states, these locations where we finally arrive at the goal. Okay, so that's what we're looking for. We're looking for some form of plan. Now, the difference, right, is our plans could look wildly different. This is, under our current ideas, also a plan. It is also a solution to the problem. We can zigzag around in the maze. Ta-da, we get to our goal location. That seems happy, right? So the other aspect of this is in the real world, right, we're always trying to achieve something. You, as the computer scientist, need to define what the objective is that we're trying to minimize or optimize. So in a pathfinding problem, oftentimes it is as simple as we want to minimize the grid distance, right? So you're looking for a path or an equivalent length path that is the shortest path. It is the smallest, the fastest way to get there. Now, this is not always simple, right? Because again, we're going to have to abstract the real world. Maybe there's different distances, there's different weights associated. Some things are easier to move through than others, so forth. But then you also might care about other things. So for example, I study pipe routing, right? So for me, bends are expensive. So even if there's a really short path, but it bends a few times, that's just, we can build in a cost objective, right? So you might care about different things, and then we would have to search and try to find a plan that takes into account these. So we're going to get to that, and we're going to move forward and soon talk about essentially how we're actually going to search over these terms that were defined here. So I hope you stick with me. Thanks for listening.